Okay, welcome. Welcome to the 29th Hintze Lecture in the Department of Physics. I'm Stephen Smartt. For those of you who don't know me, I'm the Philip Wetton Professor of Astrophysics, a position generously funded by Philip and Roswitha Wetton, who are both with us tonight. I'm the Director of the Hintze Center for Astrophysical Surveys. It's a very exciting time for us with the construction and operation of a number of new telescopes and instruments that are going to shape the field of astronomy for the next decade. This is the 29th lecture in the series, just one short of our 30th anniversary. So 29th lecture, we've got, the next one's our 30th anniversary. It's a pleasure to thank Lord Michael Hintze and Lady Dorothy Hintze for their ongoing support of the Hintze Center here through the Hintze Family Charitable Foundation. Thank you particularly for the further gift to fund the operations for the next 3 years. It's a very interesting time in how humans are revolutionizing our surveys of the sky. We're going to hire some very talented people in the Hintze Center, and we expect they may change the field in some way. This combination of new instruments, new telescopes that we're building on Earth, and as you'll hear in space, the DPhil students and postdocs that the Hintze Center supports, and novel ways of surveying the sky, I'm sure will lead to new exciting results. So as you're going to hear, we can look deep into the universe, not just for the first glimpses of galaxies, but extraordinary detail of cosmic dawn. And also in Chile, we have the Vera Rubin Observatory, which is in the final stages of commissioning. This is as large as the James Webb Space Telescope in terms of its mirror, but it's not as sensitive because it's on the ground. But it has a camera which is 1,000 times larger than the James Webb camera, as you'll hear. So we'll look at the sky in a different way. And we're going to have an event to celebrate that here on Monday, the 23rd of June, so look out for that. The Hintze Center has funded our preparatory work for Rubin, and we're ready for the enormous data flow from that telescope. So with that link, it's a pleasure to welcome our 29th Hintze speaker, Professor James Dunlop from University of Edinburgh. Jim was a physics undergrad at the University of Dundee and then completed his PhD in Edinburgh in 1998 under the supervision of John Peacock, who some of you know. Jim was John's first student.
88. I'd like to say it was 98.
Oh, sorry. Are you sure?
Yeah, no, it was
okay.
fine.
It was eating. So high redshift evolution of radio galaxies and quasars. And so Jim and John was here here a few weeks ago when he told me Jim was his first PhD student. I think he said the most successful, but don't quote me on that. Right. So Jim, as far as I can tell, had no postdoc career. He went straight to a lectureship and reader positions at University of Central Lancashire and Liverpool. John Moores, he set up the group, or helped set up the group in Liverpool. And after that, after a year, he had 1 year or 1 or 2 years in Canada as a Canadian research professor, but he's been at Edinburgh ever since 1995. So Jim's been awarded an impressive number of national and international prizes, the George Darwin Lectureship and the Herschel Medal of the Royal Astronomical Society. He was elected a Fellow of the Royal Society in 2016. And he's made many scientific discoveries in the area of galaxy formation in the early universe. But he's also shaped the UK's position in this field, not just his own research, but the UK's direction. He chaired one of the most important panels at the start of around 2000 that made a successful bid for the UK to join the European Southern Observatory, and he's led major projects with many of the UK's leading telescopes. Jim is also about to become the principal investigator for Harmony, an instrument that the UK are funding and building for the extremely large telescope. This is an enormous 39-meter optical infrared telescope, the largest ever built, and likely the largest will be built for the next 100 years, probably. The Harmony concept was born here in Oxford. Niranjan Thati led the inception and design of this instrument. He secured the UK funding and drove the project to where it is today. I would say this is the most scientifically capable instrument concept for the ELT. And the Oxford team are here tonight. I'd like to pay tribute to them and Niranjan, Fraser Clark, Matthias Teska in particular. They developed the idea and made it a reality. We wouldn't be here today if it wasn't for their vision and Niranjan's vision and drive to put this team together. And we look forward to working with Jim in the future in this next phase of building the instrument. So that's for another day. In about 10 years' time, that instrument will hopefully be delivered. But Jim is here to talk to us about what he has done with the James Webb Space Telescope, a really remarkable facility. So Jim, it's a pleasure to welcome you here as the 29th Hintze Lecture.
Thank you, Stephen. Very kind words. And thank you, Lord Michael Hintze. I'm sorry not to meet your wife on this occasion. I'm not really going to talk just about what I've done. I'm going to talk about what various people have done with the James Webb, which you can see the picture here. There'll be a bit of an Edinburgh bias, but that's just because these are the areas of work that I know most directly about. I'm aware that everyone in the audience is from people who know science to people who know more than I do. So I'm hoping there'll be something for everybody. The plan here will be a little bit of scene setting. And I gave a similar lecture like this in Edinburgh a few months ago, and I thought it went really well. And at the end, the support staff who'd come for it are not scientists. And I said, "Did you like that?" And they said, "That video you showed, was that pictures of cornflakes or galaxies?" And so you'll see that video, and if you think it looks like cornflakes, you'll know what's going on. So that just proves that you can't satisfy all the people all of the time, but we'll see. Hopefully there'll be something for everybody. It's an exciting time to be doing this work, and Stephen talked about other projects, some to come, some large survey projects about to happen. But there's no denying that at the moment we're lucky in this area of physics and astrophysics to have a machine that is revolutionizing the subject pretty much every week. And you know, this is the kind of talk where I can show you at one point the spectrum of the most distant known object, which was discovered in May. Okay? So it's not often that people can stand up at physics lectures and talk about something at this level of the cutting edge. So in a way, it's an easy talk to give. I'll try and blend some motivation. Some people here might come to these talks who are engineers. I'll also talk a little bit about the amazing thing that is the James Webb Space Telescope and how, frankly, mental it is that it works. Okay? And so there's some fun there to have. I've also got some absolutely rubbish props here. At some point, I'll kick this up the back and somebody can hold the sun. I had a globe and it wouldn't go into my hand luggage, so Stephen said, "Oh, we can help with that." This is Stephen's best attempt to help with a globe. And then this is the worst bit. I ordered a model of the James Webb Space Telescope, but it arrived and it was that size. So I decided to make one out of kitchen foil, and a panel is broken off between Edinburgh and Heathrow. So how they can get that to Lagrange point 2 million miles from Earth, and I can't get the James Webb Space Telescope from Edinburgh to London. Well, anyway, this will be good enough for the points I want to make. I think it was partly because I was just too excited coming off the flight, because thanks to Michael and the foundation, this is the only time in my life I've walked into an airport arrivals hall and somebody was holding my name. And beside him was somebody holding Mr. Gary Player. So if you don't know, I can't help you if you don't know who Gary Player is. But we were chatting on the flight about golf, Scotland, South African politics, all sorts. And the two of us emerged into Heathrow to name. So I thought, at that point, it was kind of done. Nothing else to do after that. Right, enough rambling. Let's see how we get on here. I'm going to try and dim the lights a bit. There's quite a bit of tech in this talk, and it may or may not work. Okay, so what we're going to talk about, we're going to talk about something that when you speak to people in the street or in the lift or wherever, you either think this is an utter waste of time or one of the most important things that human endeavour can tackle. This is an origin story about the first things that ever formed, and in the process, the first elements beyond the hydrogen and helium that was made in the Big Bang that were ever formed by the first stars in the first galaxies. So at some level, it's almost bordering on philosophy rather than science. We're trying to say, where did we come from? And This is the kind of cheap and cheerful version of why you should care about this, even if you don't care about astronomy. I mean, we're trying to hide carbon all the time now, but the carbon and the oxygen, this is a better set of lungs than mine. The iron that get the blood around, that carry the oxygen around your blood, the iron that underpins so much of our famous civil engineering, and then progress towards peak achievement in life. Certainly that was after I'd climbed a mountain. That's a photograph of my lager at the end of Loch Tay, which obviously requires carbon and oxygen as well as the hydrogen. So you couldn't have this without the first stars, okay? And that's maybe not the best motivation, but it's our motivation. Oh, damn it. Not sure these lights are going down. The screen's bright enough anyway, okay. So what's going on here? Well, we now have this rich periodic table of elements that we'll talk about in a minute. This is an image of the early universe, and this is not going to be a cosmology talk, but you'll have seen many of these talks. An image of the microwave sky taken with the Planck satellite. And the point of this is here that you see the seeds, some unevenness in the early universe, and it's just as well there's some unevenness, otherwise there would be no seeds for gravity to get a grip and make the first structure. It's worth reminding us here, though, that this image of the universe, which is the furthest back we can look directly, earlier than that we have to infer things, but not through direct astronomy imaging. 400,000 years after the Big Bang, at this point the universe is flat to the part in 1 point in 100,000. So if you've a meter-high table, then glass is still not as smooth as the universe was, relatively speaking, at this point. So these images always exaggerate the amount of structure. But there was structure there. On the other hand, I've used the phrase 15-minute stir-fry here, because in terms of what actually was done in terms of making the elements, the universe during the Big Bang, or just after the Big Bang, was only hot enough for about 15 minutes to fuse some hydrogen into helium. So it really is, I don't mean pretend it's 15 minutes, I mean an actual 15 minutes before the expansion of the universe made things too cold for nuclear reactions to keep going. It's important because this means that although the Big Bang is great, if you're trying to make the richness of the world around us, the periodic table, the blood, your alcohol, your laptop, the Big Bang didn't help very much. You might say, well, that's not the job of the Big Bang, it was just to create the universe, but that's fine. So the question then becomes, how did you get other elements in the universe? And if you think of the Big Bang as a stir-fry, then the stars are the slow cookers of the universe. And in the center of stars like our sun, temperatures and pressures get high enough to fuse hydrogen into helium, then to fuse helium into carbon, and then you get nitrogen and oxygen, and eventually all the way to iron. And this isn't going to be a talk about the origin and evolution of the chemical elements, but in the end, stars or their remnants or their final explosions generate everything that you see in the periodic table, apart from things that are produced by radioactive decay. These days, I mean, 10 years ago, you didn't used to see periodic tables like this. You like to think that in every chemistry class at school, there's now a periodic table with some idea about where the elements came from. So we have hydrogen and helium, mainly made in the Big Bang. Everything else, you see different versions of this plot, and it changes a lot. People are still arguing where most of the gold came from, for example. But you can see a lot of the elements, the simple elements like carbon, nitrogen, oxygen, these things are made mainly in exploding massive stars. And some of them must be made very early in the universe, in the first massive stars that exploded. This is actually quite a complicated diagram. Beryllium, we'll come back to that. The mirror of the James Webb Space Telescope is made of beryllium. It's not made in stars. It's a bit weird. In fact, beryllium-8 is completely unstable, so we might come back to that as a kind of quiz question. Where on earth did you manage to make the beryllium for the James Webb Space Telescope mirror? So there's different motivations. Astrophysicists are sometimes interested in how the first stars formed. Some people get very excited about reionization when the universe heated up and all the hydrogen was ionized. But a basic motivation that I think is often very effective is just saying, where did this richness come? not just the structural richness of the universe, but the chemical richness come from. Now, we know nowadays, here's the famous Hubble picture of the Eagle Nebula, voted by somebody, the astronomy picture of the 20th century. We know nowadays in our galaxy that stars form in areas of gas and dust, where the dust made of silicon and carbon helps to radiate away the energy and helps the stars to collapse. But there's an immediate challenge here, really, which is there was no dust, no cosmic dust, no oxygen or carbon or anything to help radiate away the kinetic energy in the early universe. So how did the first stars form? And again, there's people here in the audience who work on the theory of first stars. At the level of interest in this talk, the main point is we think that the first stars formed in the universe were really enormous, probably a couple of hundred solar mass stars. So call it 100 times more massive than the sun. That's for reasons to do with the cooling if you don't have these other elements. And so we know that massive stars, you might say, well, there's lots of fuel to burn, but actually it's a bit like a Rolls Royce. There may be lots of fuel, but it's very expensive to run. And so they live fast and they die young, exploding in supernova in something like 1 million years. What's a supernova? Well, here's a famous one from 1987, about the time I did actually get my PhD, sadly. So it's a bright object where you go back and you look in previous pictures and it just looks like a fairly ordinary star before it exploded. One of the fun things is this is not in our galaxy, but in the Large Magellanic Cloud, a nearby galaxy. It's close enough that since 1987, you can actually see the ring of debris coming out from the supernova. So there's a photograph made by the Hubble Space Telescope in 2003, and we've not really got to the James Webb Space Telescope, but there 20 years later is the James Webb Space Telescope of supernova 1987A. So this is sort of astrophysics in action, where you can see the debris from the explosion being recycled into the interstellar medium, and quite a lot of the elements made in this star when it exploded are then ejected into these rings and then go around into another generation of stars. I've said it's quite close. This will come up. Actually, this object didn't blow up in 1987. It blew up in 1987 minus 168,000 years, because that's how long the light from the Large Magellanic Cloud takes to get to us here on Earth. So this is the first point. I'm going to try and emphasize this point about astronomy as time machines looking back in time. And it's just a kind of cartoon of what's going on in a star before it explodes and goes supernova. Once the core of the star becomes iron, further fusion of iron is unstable, and so the star basically collapses and you get a black hole or a neutron star. Something dense is left in the middle, and lots of the ejecta is ejected out into the interstellar medium. So one annoying thing about astronomy, and because I didn't do any astronomy until after my first degree, it still annoys me. Astronomers do everything backwards. So the first stars in the universe are called population 3 stars. The next stars in the universe are called population 2 stars, and something like our sun is a population 1 star. Okay? It's a good rule of thumb in astronomy that anything that seems sensible to measure will be done backwards. So population 3 stars, it's a weird thing. We know they must have happened, but they've not been seen yet, and they might be very hard to see, because if they really were these very massive stars, they wouldn't last very long. But part of the point of this talk is people, and there's several people here in the room working hard on this in Oxford, when you're looking back in time to the first galaxies and stars, this is a kind of holy grail to see the first generation of stars, which should have been made just out of hydrogen and helium from the Big Bang, and would be the first things that produce the oxygen, the carbon, more helium, etc., to make the next generation of stars. So at some level, when people talk about first light, they also mean, can we find population 3 stars? Okay, a little bit of change of gear. Just to remind people that astronomers like myself don't look at tiny faraway things because we like it. We look at tiny, faint, faraway things because that's a way to see back into time. Okay? If we could do this without doing that, we wouldn't be building massive telescopes, trying to grab every photon of light. So this is a kind of perspective section. It's amazing how many people understand that sound has a finite speed. They're used to seeing the lightning from a storm and counting to 5 for the thunder to arrive if it's a mile away. But it's harder to get your head around the fact that light has a finite speed. Now, those of us who work in physics, this is kind of well accepted, and we all know the history of how it was proven. But it is worth remembering that light is really quick. So here's the Hubble Space Telescope. This is to make a couple of points, really. The Hubble Space Telescope is 2.4 meters wide, so the diameter of the mirror is about the same as this wooden platform. It's obviously been transformational. When it was made, it was the worst telescope ever made. Actually true. I think since Galileo, it was the worst telescope ever made. But it was fixed, and that's another story, and is still performing surprisingly well. The relevant thing here is it's incredibly close to the Earth. You can see that. There's the Earth's curvature. Enough that I hope there's no flat earthers in the room. You can see some curvature. It's only 350 miles up above the Earth. That's good because the shuttle astronauts could go and fix it. It's bad for two reasons. One is it's a warm telescope bathed in the warmth from the Earth. So you can't really do serious infrared astronomy where you need something colder. The other thing is it rattles around the Earth about once every 90 minutes or so. And so scheduling with the Hubble Space Telescope is really difficult because you're looking at an object over there and then the telescope's over there 30 minutes later. Light travel time from the Hubble Space Telescope is 2 milliseconds. Pretty much instantaneous. Light travel time from the moon. When you see the moon, if it disappeared inexplicably, you wouldn't know for 1.3 seconds. That's how long the light takes to get to us. Usual, more obvious point made here. This is one of these stupid diagrams that makes it look as if the Earth is, you're all about to die. That's the relative size of the Earth, but it's not there, right? We'll come back to that. 8 minutes from the sun is the light travel time. So you still might not be that worried about it. Jupiter varies in its orbit a little bit, half an hour to an hour till you get light from Jupiter. Jump through all the planets. This is not a solar system talk. And we won't have an argument about whether Pluto's a planet or not, right? It's a planet, it's fine. The people arguing about this have too much time. It takes, what does I say it takes here? 5 hours to reach us, so that's basically of order the size of the solar system. And it's worth saying that one of the fastest things we've ever built took 10 years to get to Pluto, so we're a long way from getting to the speed of light in spacecrafts, and a rather beautiful picture of Pluto that as recently as 10 years ago came in for the first time. Okay, so that's like, you might say, well, 5 hours, I see Pluto as it was 5 hours ago. Things get pretty hairy pretty quickly when you go to the next galaxy. So the next big city of basically 100 billion stars, Andromeda Nebula, a bit like our Milky Way, we reckon, if we get out of our Milky Way and look at it. You see M31 as it was 2.5 million years ago, and that's the closest galaxy. So suddenly we go from hours in the solar system to 2 million years. So people often, at this point, someday in your typical astronomy society says, are there aliens in M31? And you point out that if you got the message and you then replied, be unlikely to be the same person you'd be talking to, because the conversation would have a lag of 5 million years. So if somebody said, we're coming to get you, they'd probably be here by now, I suppose. Galaxy clusters, another beautiful Hubble image. You see these galaxies as they are 5 billion years ago. So many of the stars in these galaxies have probably died in the intervening period. So you get into this interesting situation where you're looking back in time to the universe as it was. You don't really know what's going on there now, but on the other hand, you've got this free history lesson. So in this big picture then, the universe is now known from various very solid, and people argue about the tensions, but the big picture that the universe is 13.7 or 13.8 billion years old. It's pretty clear. I already showed you a picture from 400,000 years after the Big Bang. We already know that before James Webb that there's plenty of galaxies about 1 billion years after the Big Bang, and so things got going quite early. And so the cartoon is that we're still to find the epoch of the first stars. Presumably they formed into the first galaxies fairly quickly. In 13 billion years, we get to the present day universe. And basically what James Webb does many things, but what we're trying to do with it in high redshift astronomy is work out what's going on here, through to here basically. This key phase in the university where you went from nothing, well, smooth stuff, to the first nuclear generators called stars, and then on into the galaxy and the complexity we see today. So there's various people do simulations of this sort of thing, and if you can't see it, why not simulate it? Sadiq Khoshfar works at Edinburgh, and he does this thing called the first billion years simulation, and that's for two reasons. One, he's interested in simulating the first billion years. The second is it's so computationally expensive you can't run it past the first billion years. So this is a simulation. He gave me a visualization of a hydrodynamical simulation where the color is by temperature and the actual image is by density. And this is, for those that care about such things, it's 4 megaparsecs by 4 megaparsecs by 4 megaparsecs co-moving. So there's a decent sized volume of the universe. It starts about 20 million years after the Big Bang and ends up about 1 billion years, as in the first billion years clue. I put some music to this, we'll see if it works, because at first, absolutely nothing happens, and it's the most boring video. The first time he sent it to me, I sent it back saying, this is a still. He said, no, it's not a video. It's not a still, it's a video, and it just takes gravity a bit of time to get going. So it went green when the universe was reionized when the temperature got to about 10,000. Apologies to Tom Cruise for stealing the music from one of his films. You can tell me afterwards if you know which one it was. Okay, so key questions we're trying to answer then. When was cosmic dawn? What did the first galaxies look like? Can we find these very first population 3 stars? And we need to find, really you can do the simulations, but in the end we need to find and study early galaxies and look back in time to answer these sort of basic questions. Right, this is the worst slide. I'm going to try and explain what redshift is here, because all the time people talk about high redshift objects. Only equation, I promise. Again, it's a slightly silly thing. Astronomers chose the symbol Z or Z to stand for the word redshift. Okay, nobody really knows why. So what is redshift? So 1 plus the redshift is the wavelength of light we observe compared to the wavelength when it was emitted. And the point about this is that if by the time we observe the light it's been stretched by a factor of 2, redshift will be 1. And there's various explanations for this, but to first order, as the light comes across the universe and the universe expands, light is not held together by the electromagnetic force itself at all, so there's no reason why the light won't expand as the universe expands. So the power of this actually is that it's not just the ratio of the wavelength of light, it's the ratio of the size of the universe now compared to the size of the universe when that light was emitted. And it's not even a shift, it's a stretch. So it should be called the redshift stretch and given some symbol R or something. Anyway. So as this light stretches, what started off as blue or UV light, as it journeys across the universe towards us, expands and expands and expands, and arrives as red light, or if it's come from a long way, arrives as infrared light. And the way we discover high redshift galaxies is shown in this cartoon. So this also doesn't sometimes work because people are, what the hell is this? So what this is a spectrum of light from a galaxy as seen through the blue filter on Hubble, the green filter on Hubble, and then other filters out into the near infrared. And what you'll see if I run the little video, this isn't actually a galaxy running away to high redshift. This is a galaxy saying what it would look like at progressively higher redshifts. And the point is that it disappears at the hydrogen absorption wavelength of 1216 angstroms, called the Lyman break. And so as the galaxy goes to higher redshift, it disappears in the blue bands and is left only in the red bands. People call these dropout galaxies because they drop out in the bluer bands as they go to higher redshift. There's the redshift running up to redshift 5, 6, 7. And so you eventually end up with an object which is extraordinarily unexciting in the blue bands because it's gone. And the reason that Hubble really couldn't see much beyond redshift 10 or so was because it didn't go red enough to see things to higher redshifts. So this is actually how people select high redshift galaxies. Okay? It almost looks ludicrously, laughably easy, and it is if you do it right. It's also possible to do it really badly. So you select these galaxies just from the imaging, and then you follow them up in more detail with spectroscopy to be sure you've seen what you think you see. This has been a story of different facilities, and don't worry, I'm not going to talk about 6 telescopes today. Hubble made huge advances. We've also done a lot of work from Stephen talked about the Extremely Large Telescope. These are deeply unimaginative names. VLT stands for the Very Large Telescope. So the next one coming is the Extremely Large Telescope. And I hate to say it, but there is a design for an overwhelmingly large telescope, which has got the advantage of the acronym OWL. Okay. Subaru Telescope in Hawaii, run by the Japanese, very successful. Keck Telescope, ALMA. In the end, though, the big change has happened since the James Webb Space Telescope was launched in Christmas 2021. And it's transformed the landscape for a couple of reasons that I'm about to explain. So, one is that it's a lot bigger than the Hubble telescope. But the key thing really is that it's a lot colder than the Hubble Space Telescope. Remember I showed you a picture of Hubble just above the Earth's surface. James Webb is about 1 million miles away from the Earth in deep space, essentially. So this is to scale. The previous infrared telescope, Spitzer, is only about 85 centimeters diameter. Here's Hubble at 2.4 meters. Here's the James Webb. Compared to this infrared Spitzer telescope, the collecting area of James Webb is up by about a factor of over 50. And this is why it's so revolutionary. Where is it? It's in a place called Lagrangian point 2, L2. This is not to scale. We'll attempt to do it to scale in a minute. Be outside of Earth here. There's 5 of these Lagrangian points. Won't get boring with the technicalities. The first 3 were discovered by Euler. Lagrange found the next 2 and must have had an excellent agent because they're all now called the 5 Lagrangian points. Okay, these are places where a spacecraft would sit in a stable or pseudo-stable place. Okay, so at this point, I have to ask. I'm going to ask Matt Jarvis, the ex-footballer, to kick this to the back, but that would be dangerous. Someone hold the sun at the back of the lecture theatre. Okay. That's the sun, and I had to inflate it today because that wouldn't fit in my luggage either. So if that's the sun, about 0.5 metre across, thank you, glamorous assistant. Very good. I should turn the lights up a bit, shouldn't I? Now, people doing public talks in astronomy always have this challenge: how do you make a scale model of the universe? If that's the sun, which is 1 million miles across. It's about half a meter. So the Earth would be 93 million miles away, 50 meters away in this scale model. And Stephen said, have you got something for the Earth? Well, I stole a grape from the grapes on level 7 of the physics building. Right. This is the sophistication of this talk, right? That's the Earth, right? Actual scale and size and distance. But that's not very good for seeing. So we'll blow that up here. Basically, that sun's about a scale model of 1 billion. Let's get the Earth up by a factor of 100 so you can see it. And at this point, bring out my crap 1 in 100 scale model of the James Webb Space Telescope, which lost a panel on the way to Heathrow. The point of this is just to say where this is. So if this is 93 million miles, the sun's about 1 million miles across. Here's James Webb. It's another 1 million miles, so about half a meter away in this scale model. Now what's clever about L2 is, not normally in the solar system, if you're further out, you fall behind. That's why a year on Jupiter is a lot longer than a year on Earth, etc. Lagrangian point 2 in some ways is dead simple. It's the exact point where the gravity of the Earth adds a little to the gravity of the sun so that it gives enough extra acceleration to James Webb to keep up. So it doesn't fall behind. In fact, it stays about 1 million miles away. Because you can probably see a problem. If that's 100 times bigger and it's 100 times further away, it'll just see the Earth eclipsing the sun all the time. So that's no use because you want solar power. So what it does is it does a halo orbit of about 1 million, a quarter of 1 million miles like this. So it can see the sun, but then it has to hide from the sun to keep it cold. So here is literally it does this about once every 6 months. This is what James Webb does in what's called a halo orbit. It's quite complicated, actually. Going around the Lagrangian point 2. But, it's not flying away into space, so you can keep talking to it, okay? And the only thing that limits the lifetime of the James Webb Space Telescope is how much fuel it requires to just keep doing tiny adjustments to stay in its halo orbit. So it's out here, it's 1 million miles away, but you can talk to it. You need to get the data off the telescope. But the sun shield keeps it cold, and it gets enough sun to run the solar panels so that it can do some power. And this is actually where all the telescopes that need to be really cold are sent now. The Planck satellite is at L2. Herschel, now decommissioned, L2. Euclid, recently launched out at L2. You might think it's getting crowded, but this orbit's about 500,000 miles wide, so it's fine. Something of interest, maybe to some people in the room, particularly those that used to be at Edinburgh, this idea of cooling down the telescope with this sun shield. I mean, my kitchen foil version is 3 layers, but the real one's got 5 layers of actual stuff that are the only right thing about this model is the thinness of my kitchen foil is the thinness of the sun shield. That's not scale, that's actual kind of small fraction of a millimeter. It used to be people thought that infrared telescopes would be very expensive because you had to keep them cold and you had to put cryogenic fridges in them all. Lovely guy, Lance and I knew him well. Other people in the room will know Tim well. He actually ended up, sadly died in 2009 and didn't see all this come to fruition. He was one of the pioneers of this idea of that you could what's called passively cool a telescope. And so this thing where you have all these layers of foil, this is Tim back in his heyday of. It shows how long these ideas take to get from gestation to truth. All this ideas about infrared telescopes in space were being done 30, 40 years ago. And here's some of Tim's diagrams. This idea where you have membrane after membrane after membrane that's really thin. And you don't have the problem of convection of heat, but you've got to keep the conduction down, so you have tiny little thin struts, and you need the different layers of the sun shield to let the radiation leak out, so the layers are slightly splayed apart at the end. This basically has to drop the temperature from boiling point of water to 40 Kelvin. And if you do that properly, you don't really need any more cooling on board James Webb except for one of the instruments which needs to be a bit colder, maybe down to 7 Kelvin. And it's interesting when you watch the engineering videos about this, engineers hate doing stuff that is flexible and moving. And this is then, somebody said it's like a parachute. You have to fold it upright, otherwise the results will be disastrous. This is then making sure they're getting the folding right, because this thing's the size of a tennis court, and it has to automatically in space expand. And the sunshield itself had 300 single failure points. So that's one thing that's surprising it worked. Okay, I'll just say some things then about the science that we've been doing with James Webb. James Webb, without trying to get too technical, has got cameras, near-infrared camera, mid-infrared camera, and crucially also spectrographs that allow you to take detailed spectra, spread out the light that you see from an object. And this is what's called the focal plane. These different instruments see different bits of the sky at the same time. So you can actually take some images of the sky through NIRCam while at the same time taking spectra of objects in a different bit of sky. And the amazing thing about Webb was immediately it was completely brilliant. It launched on Christmas Day 2021. First real data came in May 2022, so pretty much three years ago from now. This was a previous picture at a wavelength of 8 microns. This is what you got with James Webb compared to what you had with Spitzer. And actually, the engineers seem to have been keeping something in reserve because the specification, it actually delivered a better telescope than was required to meet the spec. This was the first NIRCam image. This is the one that was shown by Joe Biden in the disastrous Zoom-failed chaos of the first press conference in the White House. But anyway, still a beautiful image. First 3-color image with NIRCam of a galaxy cluster. So the cameras work beautifully. So I'll just show you some highlights from JWST imaging and then a few things from JWST spectroscopy. Imaging doesn't contain as much information as the spectroscopy, but it's easier to detect the things because you're letting all the light in quite broad bands. So you use it to find the galaxies. You can estimate the redshift, as I showed you from the dropout effect, just from the imaging. And obviously you can count them and do a statistics and population census. And you find out targets that you're going to follow up later. And one of the good things is we've managed to persuade the James Webb Space Telescope time allocation people to do some of these big imaging surveys early in the mission. Because it was possible JWST would only last for 5 years. I mean, obviously something disastrous could still happen. But the idea was to do some of this imaging early on so you could follow it up with spectroscopy. The one that I was PI of, it's called the Public, I'm trying to remember what it's called, it's a good name, Primer. Yeah, I remember now, I did make it up. Public Release Imaging for Extragalactic Research, and we produced a logo that looks like a primer pot of paint. I thought it was absolutely brilliant. Apparently nobody in the US knew what I was talking about at all. In America, they don't call the first layer of paint primer, anyway. So this is many, many pointings with NIRCam covering about 400 square arc minutes in total. And with all the redshift information here, we can do a fly-through and see what this looks like. And you should notice that by redshift 10, there's not many galaxies left. So this is a real 3D fly-through image. That's the sort of exciting version. What you actually do is you make a map with a survey, you combine it with some deeper, smaller area surveys, and you try to do a census of what the galaxy population is doing. And Callum Donnan finished his PhD with me at Christmas, and working a lot with Ross McClure, one of my long-standing colleagues, was working on this to do basically the population evolution of the galaxy population. Anecdotal for people in the room, Fergus probably won't thank me for this. So Callum's twin is in the audience. Is Fergus here? Okay, this is them graduating at St Andrews. Not identical twins, which is useful because I didn't mistake Fergus today for Callum. Anyway, both amazingly doing science with the JWST and off to do their postdocs in America. What you get out of this, without getting technical, are so-called luminosity functions. At different redshifts, so looking back in time, you can map out how common the galaxies are. So these are faint galaxies. This is backwards as usual. The faint galaxies down here, and the bright galaxies an even bigger negative number. But this is basically just population statistics for galaxies. Okay, like making a census of the height of people in the UK, except in galaxies, faint ones are always much more common than bright ones. And this is the first time James Webb has made it possible to look at the population of galaxies at redshift 9, 10, 11, 12 and a half, things that were unachievable with Hubble. And then when you collapse these functions on themselves, do a luminosity weighted integral to be technical, what you get is the density of UV light as a function of redshift, so this is going back and back in time, which you convert into how many stars were being formed each year per unit volume in the universe. Crudely speaking, this just shows activity declining as we look back and back. And without getting too worried about the technicalities, at some point you hope to see nothing. Right? The goal of this work is to suddenly see no more galaxies, because then you'd have got to the... And the big surprise for lots of people is, as we move back in redshift made possible by James Webb, we still keep seeing tons of action. And the question, there's a big question here. People are arguing now, are there any galaxies beyond redshift 15? Because we haven't found any yet. This is to show why you have to do observational astronomy. These are the different theoretical predictions as to what this plot should have looked like before there was any actual data to sort it out. So we're already changing people's view of galaxy formation models. And the big question is, there's some feeling, different people in the room even might dispute this, but it may be possible we're actually getting to the point of the first galaxies because there's some sign of a drop-off. We find it really hard to find galaxies at 15. And this isn't because James Webb shouldn't be able to see them. It can get red enough to see them. It's turning out to be very hard to see them. And there's a lot of arguments going on at the moment as to whether this might be the epoch of the first galaxies, we'll see. So is this... I should be careful what I say at this point because this is going to go on YouTube apparently. There are various papers claiming to be redshift 25 galaxies, redshift 17 galaxies, and even a redshift 30 galaxy. I think they're all wrong. And there's certainly no spectrum confirming any galaxy beyond redshift 15 yet. One of my postdocs, Derek McLeod, lovely guy, he has re-reduced every image taken with JWST in the last 3 years to get coverage over half a square degree. And he has only found one possible redshift 15 galaxy, and we've been given time on NURSPEC to check this out. Probably in July, we thought November, but apparently they're going to try and schedule it in July. The downside of this is what Derek looked like before this effort. That's what happened to Derek after this effort. He's still smiling, okay? Okay, but this is hard work, and to do this work, you've got to trawl through tons of data, check all the candidates really carefully, etc. Anyway, okay, so that's what we're doing with imaging. We haven't yet found convincing candidates beyond redshift 15. I think the next year will tell us if that really is an important step change epoch. Spectroscopy, okay. I'm going to go on for another 10 minutes because Stephen took so long to speak at the beginning. Hope that's okay. What is spectroscopy? Well, you know it from album covers, at least if you're as old as me. You spread out the light with the prism into its constituent colours, and in these different colours, There's lots of information, including the fingerprints of the different elements. Apparently this is wrong. Somebody with too much time in their hand published a paper in Physics World showing what the cover of Dark Side of the Moon should have looked like. All the angles are wrong. Anyway, there it is. It's a kind of facetious point that it's taken somebody till 2023 to undermine the album cover. But anyway, in their spec in JWST, there's an amazing instrument I just didn't think would work. There's a thing called the Multi-Micro Shutter Array, MSA, which is lots of little pockets where they can open a door if you want to let the light in from a galaxy at that particular point. So you can actually take, as the name implies, multiple spectra. So what the spectra look like are this, and then you turn that into a 1D trace to see what the spectra are telling you. So this amazing instrument is way more complicated than anything that's been put onto any of the other telescopes out as far away as Lagrangian point 2, and it works. This is not my work here. There's people who in the audience have done this. These are some of the spectra of the most distant known objects in the universe. So the spectrum looks like this, but then when you project it into a 1D trace, it looks like this. And because you know the wavelengths that these things are in the lab, you can see lines from oxygen, nitrogen, neon, carbon, etc. So these are galaxies, back right at, 350 mega years. Remember, the universe is about 14 billion years old. Only 350 mega years. These galaxies are already full of all the chemicals, the chemical nuclei that we were talking about trying to find. So there's plenty of carbon and oxygen there. Up until last month, this was the most distant known galaxy. It's hard work. You can't see many lines, but you can see this Lyman break that I talked about right at the start. This is a redshift 14.3. And for those interested in the room, you can also go after it with ALMA at sub-millimeter wavelengths. So it's way too technical for this, but this has actually delivered the accurate redshift for this object. And then last month, shows how hard life gets, this somewhat ratty-looking spectrum, but it's definitely correct. This is now the most distant known galaxy in the universe with a spectrum at redshift 14.44. Okay, so about 250 million years after the Big Bang. It's still in the archive, being refereed. For those who don't know, 2505 means it's published in 2025, 5 for May, and rather scarily, paper number 10,000 and whatever, which is why it's so difficult to keep up at the moment. So you can see the object coming into the MSA and then giving you the spectrum. The other thing, just highlights some of the other things you get out of the spectroscopy. There's a picture of Adam Karnal. He's a new academic at Edinburgh. This spectrum is highlighted as the top result from the first year of James Webb. This is actually a more modest redshift, about redshift 5. But this spectrum is of an old galaxy, which when you say, well, when must it have formed? It appears to be beyond redshift 10. And people were pretty astounded by this, because the black line here is a theoretical model, and the blue line here is the data. And until James Webb, nobody had seen a near-infrared spectrum, anything like this. So at the moment, we're doing spectroscopy, following up all the sources in Primer, a couple of programs here. Another good fun highlight recently is the discovery of these little red dots, which were unknown before James Webb. These are very compact objects. The clue's in the name. They are little red dots. So even with the power of James Webb, they look point-like and very red. And there's a raging argument going on about whether these are compact galaxies or actually growing black holes in the early universe. And this is going to take a lot of work to sort out. The highest redshift little red dot has got the red because the spectrum goes rocketing up here. They've got these strong lines. People think it's black hole accretion. And then they've got some blue light here. This is a classic example of an object that nobody knew existed, and now there turn out to be thousands of them in the early universe. It shows how parameter space is opened up when you've got a new instrument. And Fergus Cullen, who's also at Edinburgh, I think it's fair to say this is the best example so far of a metal poor galaxy. It's not population 3. We can still see some oxygen, but the elements are down at the level of 1% of what the chemical enrichment of the sun is. Okay? So this is the closest step we've got to something that is close to being a primeval galaxy. And the spectrum of a population three star is meant to be this blue thing here. It's not quite as blue, but it's getting there. And so we're getting closer to seeing relatively metal-poor objects. It may be that we'll never see a population 3 star, he says rather depressingly. We'll see, just because they don't last very long. The best we might manage is something just in the immediate aftermath of a population 3 starburst. Still plenty of time though. Closing thoughts and reflections. I was thinking about how much this, this all was happening just before Christmas 2021. Don't know if you can remember what you were doing just before Christmas 2021. It's worth remembering that this had to be smuggled through the Panama Canal, at that point still called the Panama Canal. Okay. Oh, sorry, this is going to be on YouTube, right? So it wasn't hijacked. I mean, terrorists actually have hijacked telescopes in the past, you might wonder, but this is a 10 billion machine. Had to be all folded up. This is all being folded up. It had to fit into the Ariane rocket because it wasn't big enough to take a 6.5 meter mirror. So apart from the sheer complexity of the project, this had to be bundled up and then unravel with, no one was going to fix this thing. No astronauts were going to go to L2 if it didn't unravel. And so we were going to have a big celebration in Edinburgh because it was scheduled to launch before Christmas, but it ended up on Christmas Day. And I'm sure there's some people in the room here who made themselves unpopular with their families by insisting on watching the ESA feed at 11 a.m. on Christmas Day when people should have been doing the Brussels sprouts or whatever. So I thought I'd just finish by reminding you probably all saw this, but I remember this being a deeply moving moment. A company from Dublin stuck some high-definition cameras onto the final stage of the Ariane rocket so that, launches usually involve rockets going into the clouds and that's it, or they go over to a simulation, right? This actual film taken by these cameras of the James Webb Space Telescope moving away, I still think is one of the most awesome things that's ever been filmed. So this is a bit strange, because this isn't Christmas, right? We're nearly at the summer solstice. Just enjoy film from Christmas a few years ago.
Happy Christmas, baby. Oh, so good to see you here. Really.
I love the simulation to finish. Allows you to listen to Chrissy Hind a bit longer. So.
I'm in a state of grace. All that sweet smell of success. Happy Christmas. Oh, we make some stupid mistakes. As creatures of little faith. The cynic knows the price of everything. Let me tell you, she knows nothing. All that is waiting to come back.
Thank you, Jim. Wonderful talk. I'm still astounded, as you are, that it works and it works so well. Questions from the audience? Yeah, Leah. Can I give Leah? I've got 2 microphone handlers.
Hi, thanks. That's great. What in theory is the earliest time that a star could have been turned on in the early universe, and has that idea changed since the deployment of these great telescopes?
It depends on your theoretical model of POP3 stuff. Now, for a long time, people have said redshift 30. So getting to the sort of stage we were talking about, but it's completely under dispute because they don't really know how things would cool properly without these other elements. Basically, you end up assuming that molecular hydrogen has to be a dominant coolant because there's no oxygen and carbon to help radiate away, turn the kinetic energy into radiative energy and get it out. I mean, the interesting thing is, so if you ask people when did the first stars form, they just used to always say about redshift 30. And that was so far away from what we could see, it was like, whatever. But now we're getting close to being able to see redshift 30. It's now starting to become...
How old would that be? Sorry?
That would be about 150 million years after, 200 million years after the Big Bang. I mean, we really are running out of time. You know, I mean, what happened with previous generations of telescopes where you would get to the most distant object you could see, and then you had to admit, it used to be you couldn't see beyond the optical because you just had silicon detectors, and then Hubble got its infrared things, couldn't see beyond redshift 10, but then Hubble couldn't see beyond redshift 10. So you were continually going, is it real, or is it just the end of our instrumentation? The difference with James Webb is if there are things at redshift 30, we can see it with James Webb, because we've not run out of these red bands to keep tracking. So.
Any other? There's one up there, Shreya.
Hello, thank you very much for the wonderful talk. But I'm wondering, what are JWST's scientific goals and achievements in addition to first galaxies and first stars in other areas of astronomy, like planets and black holes and all other things? Thank you. Maybe just a brief.
Yeah, well, out of my area, but it's pouring a lot of time into trying to look at exoplanets and the atmospheres of exoplanets. maybe other people in the audience should shout about what else James Webb's doing. I mean, in terms of galaxies, it's doing a lot at all redshifts, not just, I've focused tonight on redshift above 10, essentially, because that was uncharted space. But it's giving, because it can see further to the red, it can do things like actually calculate, or estimate properly the masses of galaxies that people didn't know before because they could just see the blue wavelengths. It's also changing our perspective of how many dust-enshrouded galaxies there are and how early dust was created in the universe. So a whole range of things, but I mean, people are also, because it's got sharper imaging than Spitzer, it can also look at stars in crowded fields like our own Milky Way. So almost everything that you can think of that requires infrared and high-quality imaging, it's changing.
Does that include our galactic center?
Yeah, although, that's if we're talking about Nobel Prizes and charting out the orbits of the stars around the black hole, it hasn't made a big impact there compared to what's already been done because you need the timescales to see the orbits of the stars. And that, we talked a bit about Harmony and ELT, that may end up being the territory of the big ground-based observatories, which can see sharper but of the huge challenges of the atmosphere.
Oh, some questions in the middle here. Leah, could you pass the mic up here?
You mentioned about the beryllium, about how that doesn't come from stars. Where does that come from then?
Yeah, that's a good question. So you start off in these basic things and you'd think at that point, if you remember your chemistry, you've got typically equal numbers of neutrons and protons. You know, like carbon has got 6 protons, carbon 12 is because there's another 6 neutrons. And helium-2, helium-4 has got 2 protons and another 2 neutrons. It's not usually until you get to the big elements, the radioactive ones, you need all these extra neutrons to stop the thing falling to bits. But it turns out beryllium-8, so beryllium's got 4 protons, and you might think it's 4 neutrons would finish the job. And there's this weird thing that things really like to be helium. So if you make beryllium, it quickly falls apart into 2 helium nuclei again. And this is this whole thing about, credited probably correctly largely to Fred Hoyle about the difficulty in getting to carbon, what's called triple alpha, getting the heliums together. So it turns out boron-8 is actually unstable, although you wouldn't think it. And so the boron that's in the James Webb Space Telescope is boron-9, 4 protons, 5 neutrons. And because it's not made naturally, it's quickly en route to carbon. It's what's called cosmic ray spallation, where basically you're knocking bits out of heavier elements to get you back down to boron. That's what's going on. So it's just this weird thing that one of these, we've already got to something really complicated at atomic number 4. Luckily there is beryllium-9, which is 6 times stiffer than steel and really is happy at low temperatures, and that's why it's in the mirror.
There's another one in the middle.
Why the cold temperature is so significant in the quality of image in the James Webb telescope, in any telescope?
Okay, yeah, so part of the quality of image is the bigger the mirror, when you don't have the confusing effects of the atmosphere, the sharper what's called the point spread function, the image quality is. So that's one thing. But the coolness is about pushing to the infrared, because by the time you get into the infrared, you're looking at heat. And so if your telescope is glowing, that's like trying to do optical astronomy under a floodlight, right, essentially. So you've got to get the temperature down so the infrared background is faint enough that you can see things glowing at that kind of temperature. Okay, I mean, there's been bigger challenges temperature-wise. In the submillimeter, you've got to get the thing down to under a Kelvin to see submillimeter wavelengths. The beauty of this is you're down to 40 Kelvin without needing any liquid nitrogen or liquid helium or anything to cool it. And so it just sits there and so-called passively cooled over a period of 6 months. And there's no reason it won't stay at 40 Kelvin forever. But basically you've got to get everything cold, because when you're looking at a highly redshifted light into the infrared, you're looking at something that's cold. So you've got to see something cold against the background. Cool. A long time ago, when Halley's Comet was last here, it was in 1988, right? I was walking up the Observatory Road at Edinburgh, and under each street light, somebody got the binoculars out to look for Halley's Comet. Okay, so that's what you don't do if you're looking for. So that's a bit like trying to do infrared astronomy with a warm telescope. And Hubble is so warm, they knew there was no point looking beyond 1.6 microns because the background is so hot in the telescope.
Steve, and then the last question will be up at the back if you run up there, Leah. So Steve first.
Thank you. Thank you for an excellent talk. I was very curious about the little red dots that you talked about, in particular, the idea that they may be some early black holes that are forming. Could you tell us a little bit more about that? I'm particularly interested in what kind of masses people had in mind for that. And could you tell us a little bit about the modeling that has been done on those thus far?
Yeah, okay, maybe we should chat a bit over wine, because you're very right to be interested in the masses, because people disagree by about 2 orders of magnitude about the black hole masses and the little red dots. I mean, the problem is it's a complicated bit of a mixed bag. We do know that some of the early galaxies are really compact, so some of them are probably galaxies dominated by the starlight. But there's a couple of things to tell you that they're probably black holes. One is that, try not to get too technical and bore everyone else here, the emission lines that come from the gas that we think is orbiting the black hole have really wide velocity widths, so you know they're going really fast. And that's a signature of gas that's in fast orbits in the core of the galaxy. The other thing is, one reason they're red, they're incredibly red, and they look redder than any stellar population from a galaxy that you've ever seen. They basically go off a cliff down to what's called the Balmer Break. And people can't produce models for the more extreme ones, certainly, where you get that with the stars. So the idea is you've got this wall of dense hydrogen around the black hole that's just absorbing all the light and taking it down to nothing. And then weirdly, some UV light starts to leak out. So at JWST resolution, they're point-like. So you can't tell from their image quality whether you're talking about a black hole, which would be point-like, or a compact galaxy. So a lot of the argument is in the width of the lines, how on earth you get this strange spectral shape from stars. It looks really difficult. And then you get into an argument about what you actually think is causing the broad lines. And there's a series of papers, again last month, I mean, this is really hot topic stuff, where if you do the conventional thing, these are lines about 2,000 kilometers per second wide. You say that these black holes are probably about 10 to the 7/10, quite big, big black holes, well ahead of the ratio of black holes and galaxies in the present day. But if you think that there's some other broadening things, electron scattering going on, then the lines themselves would be much narrower and the black hole masses go down by 2 decades. It's all to play for.
They're AGN scale black holes.
Yeah. No, we're not talking stellar remnants. We're talking about, are they a million solar masses or are they 10 to the 8 solar masses?
And final question at the very back.
I fear you may have just answered this, but these early galaxies, are they all elliptical galaxies? They're going to be any galaxies that look similar to ours in the early? Are they kind of the first stars collapsing into black holes, and then they start to drag these other early stars to form these galaxies? Is that the kind of theory that you'd imagine? So the first stars are kind of, we won't see those, but we will see the first time they start to form around the early black holes?
Maybe. I mean, there are not things in the early universe that look like modern day giant elliptical galaxies. Okay? But there are very compact things that might end up the cores of today's elliptical galaxies. But as people look harder at the morphologies and look at the dynamics, most of the very high redshifts look like disks, rotating disks. And this is regarded by some people as a bit of a surprise. It's maybe not. Maybe slightly puffy, hot disks, not quite as thin as the Milky Way disk. But most of for the ones that have been studied in detail, where you can look at the dynamics from the velocities of the lines, they appear to be rotating baby disk galaxies.
So thank you, Jim. I mean, I didn't appreciate actually one of the most profound things JWST might find is what it doesn't see beyond redshift 15.
Yeah.
So I think in the next few months to a year, we'll all be looking to see if you or one of the other teams detected galaxies beyond Redshift 15.
Yeah, I mean, here we've got Axina and Alex are here. Andy Bunker, I don't think is here, but it's important to understand there's lots of projects working in this sort of area.
Yeah.
And it's what's the ESO phrase? Cooperation. There's some word that tries to pretend that we're getting on, but in competition. But
I'm sure you are. So
it's all healthy, right?
So please, thanks. I'm going to thank Jim again, but please afterwards, afterwards, join us for a glass of wine or refreshments outside. And thank you, Jim, for a wonderful talk.
Thanks, Steve.